Welcome to the lecture series on digital electronics 18EC302C. In today's lecture, we are going to discuss about few more characteristics of the logic family. So, previous lecture we have listed what are all the important characteristics of the logic family, and we have discussed about logic levels and the voltage requirements in the previous lecture. And today we'll discuss a few more important characteristics that are required to know about the logic families. In today's lecture, we are going to see some more characteristics in detail. And the first characteristics of the logic family that we are going to discuss today is the propagation delay. So the name itself suggests that there will be a delay while something is propagating. So we know that in digital circuits we'll apply an input signal, and depending on the logic circuit will get an output signal, but you see that will not get the output signal instantaneously when we apply the input signal. So that means there exists a time lag between the application of input signal and resulting output signal for a digital circuit. Or we can say that the logic signal experiences a delay in going through the circuit. That means from input to the output, while the signal is modified from input to output, it takes some time, but the change is not instantaneous. That means the outputs for a digital circuit will not appear instantaneously when the input signals are applied. So this time lag between the appearance of output signals, the appearance of signals at the output of digital circuit to the application of input signals at the input of digital circuits is called propagation delay. Or in other words, I can also say the time taken for the output of the logic gate to change after the inputs have changed. So this I define as the propagation delay of a logic gate. That means the output will appear after some time you change inputs, or after some time you apply inputs, and this gap is called as propagation delay. So it is the transition time for the signal to propagate from input to output, you can say. And you can see that this propagation delay, see, the output of the digital logic gate sometimes goes low. So previously it is at high state, and now after the application of input it may go to low. And in other situation, the previous output is low, and after applying the inputs, the output may go high. And you can see that in these two cases, when the output is changing from high to low, and when output changes from low to high, you can see that the amount of delay is different. The amount of propagation delay is different when signal changes from high to low or low to high at the output of logic gate. So that is why we'll try to calculate, or we look at the propagation delay in two ways, or in two types. One type of propagation delay is the time for the signal to change from, you can see at the top, so here the signal is changing from 0 to low to high, and after that inputs have changed and it is changing from high to low. So this is actually, this is the input which is changing from low to high, and after some time it is changing from high to low. And you can see that this is the output signal of a logic gate, and you can see that the output is changing from high to low, and after some time when the inputs have changed, it is changing from low to high again. And you can see that the input is changing at this point of instant of time, but the output is changing at this instant of time after certain delay. You can see that the transition of the input from low to high is not instantaneous. So ideally it will be instantaneous theoretically, but practically the change of signal from 0 to 1 is not instantaneous, but it will take some time. So similarly, when the input changes from low to high, here the output changes from high to low, but after certain amount of delay. And similarly, when the input changes from high to low, the output changes from low to high, but after certain amount of delay. And you can see that we haven't calculated the time gap between the change in output to the change in input at this instant. We have not calculated, we are not observing between these two instants, but we are observing at the 50% of transition points for both input and output. So when input is changing from low to high, so this is the 50% transition point, and when output is changing from high to low, this is the 50% transition point. So the time gap between these 50% transition point of input and 50% transition point of output, when the signal is changing, when the output signal is changing from high to low, when the output signal is changing from high to low, the time gap between the 50% transitions of the output and input, that we designate as high to low propagation delay. So this is the delay between the 50% transition points of output and input. And you can see that there is a time gap between the change in the output signal to the change in the input signal. So TPHL is here the propagation delay of the logic gate when the output is changing from high to low. When the output is changing from high to low, TPHL gives the propagation delay of the logic gate when it is measured between 50% transition points of the input and output signal. Similarly, we can also measure the propagation delay of the signal for a logic gate when the output is changing from low to high. When the output is changing from low to high. So when the output signal is changing from low to high, this propagation delay between the input signal and the output signal when measured between the 50% transition points is called as TPLH. So here it is written as TPHL, but it is TPLH, propagation delay when the output changes from low to high, that is TPLH. So these are the two measurements for the propagation delay that we take when output changes from high to low and also low to high. So then why we are taking two measurements, or not both the propagation delays are same? No. So the answer is the logic gate takes or provides different amount of delay when the output changes from high to low and when output changes from low to high. So to know what is the overall delay, or to know what is the average delay, we have to take the average of this low to high propagation delay and high to low propagation delay. So if we take the average of these two timings, that is TPLH. So if the average of the two propagation delays TPLH and TPHL is taken, and that gives the average propagation delay of the logic gate, or simply it is called as propagation delay of the logic gate. So every signal experiences some amount of delay when it is passing through a logic gate, and that delay is calculated by observing the input signal and the corresponding output signal, by which we can measure TPHL and TPLH. And after measuring these two, if we take an average, that gives the delay experienced by the signal when it is propagating through the logic gate, and it is called the propagation delay of the logic gate. So this propagation delay, so what is the propagation delay? Actually, it's a delay experienced by the signal when it is traveling, and it is coming, when it is going from input to output. You have to see that. So if the propagation delay is large, that means if there is a large delay, then what is the meaning of the logic delay? That means the logic gate is slower, it is operating slower. So if the propagation delay is more, the logic gate is slow. We say that the logic gate is slow. So, so we do not want the logic gate to operate slow. That means it has to give faster outputs when we apply inputs. That means the propagation delay must be less for a logic gate to be faster. So we normally prefer the low propagation delays for a logic gate. So next we'll discuss few more important characteristics. One is power dissipation. So like every circuit, electrical circuit, the digital logic circuit will also consume power when, and this power is different. The power consumed by the logic gate is different depending on the type of input signals. So that's why we'll calculate the average power or we calculate the DC power dissipation, and this DC power dissipation is the product of the DC supply voltage that we apply to the logic circuit and the average current consumed from the supply. So if you take the product of these two, it will give us the average power or DC power dissipation by the logic gate. And we see that to we always try to minimize, and we always require a circuit which has less power dissipation so that it will consume less amount of power. So logic gates or logic circuits with less power dissipation are preferred. Well, and this power dissipation normally for logic gates it will be expressed in terms of milliwatts, and previously we have seen the propagation delay. So here the delay is expressed in terms of nanoseconds. So though we are saying that there is some time gap between appearance of the output and applying input, so this delay will be in nanoseconds. So the propagation delay will be in nanoseconds for a typical logic gate. The power dissipation will be measured in milliwatts. So there is one more characteristics that combines these two, the effect of these two characteristics, and it is used to compare between the logic gates of different families, and that is called figure of merit or speed power product. And this speed power product is obtained by taking the product of the propagation delay in nanoseconds and the power dissipation expressed in milliwatts. And the final units for the measurement of this speed power product are picojoules. And this characteristics will be helpful in choosing particular logic gate over the other in the to realize a given digital circuit. So next we have one more characteristics, that is fan-in. So fan-in gives the measure, it gives us uh, it tells us the how many number of inputs or what is the maximum number of inputs that can be connected to logic gate without impairing its normal operation. So that means, see, we cannot connect any number of inputs to a logic gate. So there is certain limit of the number of inputs that can be connected to logic gate. and this depends on the current requirements. So depending on the logic family, the maximum number of inputs that can be connected without degrading the performance of the logic gate is specified by the characteristic which is called fan-in. So for example, if I say the fan-in of a certain logic gate is 4, that means I should not connect more than 4 inputs for the logic gate. So if I connect 5 inputs for the logic gate which is greater than the fan-in of that, then I do not guarantee the correctness of the operation of the logic gate. It may operate incorrectly or may not. So in the same way, we have one more characteristics that is defined for the logic family, and that is a fan out. So here fan out refers to similar to the number of inputs of the logic gate, so which cannot be chosen randomly. So similarly, we cannot take number of outputs from a logic gate, and I cannot say the logic gate cannot drive any number of outputs. So there is a specific limit to the number of outputs of the gate that it can drive without degrading its normal operation, and that maximum number is specified as fan out. So here this fan in and fan out gives us what is the maximum number of inputs that can be connected, and what are the maximum number of outputs that the logic gate can drive without impairing its normal operation. So by this, it will be helpful for us to make use of this fan in and fan out information to connect the required number of uh, the suitable number of inputs for a particular logic gate. So these are all the characteristics that we have seen so far, and all these characteristics of the logic family are very important, and they are used to compare the logic gates between the various families. And in one form of circuit, one characteristic will be given importance. That means in while making one digital circuit, the power dissipation may be of importance. That means the circuit should operate at low power, and the power dissipation characteristic is more important. And the other circuit, the speed is important. So in that case, the propagation delay must be less. So we cannot have both power dissipation and the propagation delay low. So if the propagation delay is low, power dissipation will be high automatically, and the power dissipation is low means the propagation delay is high. So depending on what are the needs of the digital circuit, so we have to choose a logic gate by comparing the two logic gates between all these parameters, and depending on the chosen parameter, we have to select particular logic gate for a given the given logic circuit. So next we will go to compare the logic gates from different families. So here, though we have learned listed so many logic families previously while giving the classification of the logic families, The most important logic families that will be used practically are TTL, CMOS and ECL logic families. So here we'll make a comparison of the three families um, by choosing by choosing various parameters and that is the characteristics of the logic families. And here we have made a comparison, and here the first comparison is the components used, so the circuit elements used. So what are the circuit elements used in the transistor logic? It is the transistor and resistors. So circuit elements are transistors and resistors in TTL family. In ECL we are using only transistors, and in CMOS family we will be using both P MOSFET and N MOSFET. We will be using both, not only one. It is complementary MOSFET family, complementary MOS family. So we will be using both. And noise margin. What is noise margin? We have seen that it is the limit on, or it is the noise tolerated by a logic gate. The amount of noise tolerated by a logic gate. So that means the noise margin is more. That means the logic gate can tolerate more amount of noise. So here the noise margin is high for the logic gates of CMOS family, and it is low for the ECL family, and it is somewhere in the mid for the TTL family. It means logic gates from the CMOS family are highly tolerant to the noise. And here one more parameter, fan out. Fan out means the number of outputs that the gate can drive without degrading its performance. So here that means how many number of outputs can be driven by a logic gate. So if it belongs to TTL family, it can drive 10 outputs. If it belongs to ECL family, it can drive 25 outputs. For CMOS logic gate, it drives 50 outputs. And you can see that CMOS family logic gates have higher fan out, and the TTL family logic gates have lower fan out. And is expressed in milliwatts, and you can see that the power dissipation should be low. The power dissipation should be low. That is, it has to consume less amount of power. And here you can see that the power dissipation is medium, 10 milliwatts for TTL and 40 to 55 milliwatts for ECL. And for CMOS it is 0.1 milliwatts. And here we always prefer a logic gate with lowest power dissipation. So here we prefer the CMOS family has the lowest power dissipation, and the ECL family has the highest power dissipation. Similarly, next parameter for comparison is the delay, propagation delay, expressed in nanoseconds. And you can see that the propagation delay is the delay experienced by the signal from input to output. So if the delay is high, the logic gate is slower, and if the delay is low, the logic gate is faster. So we always prefer the propagation logic gate with propagation delay, the logic gate with lowest propagation delay. So here you can see that it is medium, the propagation delay is medium, 10 nanoseconds for TTL and 0.75 to 2 nanoseconds for ECL and 70 nanoseconds for CMOS family logic gates. And so you can see here, I can say that the ECL family is the fastest family and the CMOS family is the slowest logic family. And next finally we see compare between the families with respect to figure of merit, which is the product of these two, the power dissipation and delay nanosecond, and the figure of merit expressed in picojoules. And here you can see that this figure of merit is around 100 for TTL, and it is around 40 to 100 for ECL, and it is very low for CMOS, which is around 0.7. And normally we will prefer the logic family with least figure of merit. So here the CMOS family has the lowest figure of merit, so it is preferred among the three families. And this is the comparison of the three logic families that are of practical use with respect to various characteristics or parameters that we have discussed previously. And depending on the requirement of the digital circuits that we want to realize, whether it requires a low power dissipation or a low propagation delay or higher fan out or low noise, so we can choose the logic gates from a particular family. Next we look at CMOS NAND gate, the circuit and its working. So here in this slide we have shown the circuit of the CMOS NAND gate. So here this circuit belongs to CMOS family. That means we'll be using both N MOSFET and P MOSFET. We'll be using at least one N MOSFET and one P MOSFET, and it belongs to the circuit belongs to say CMOS family. And here in particular we are seeing the NAND gate. We are seeing a circuit, a logic circuit. We are seeing circuit diagram for the NAND gate from CMOS family. So here you can see that the circuit arrangement for the CMOS NAND gate is shown here. So here we have two P MOSFETs, Q1 and Q2, and along with these two PMOS we have two N MOSFETs, Q3 and Q4. And since it is a two input NAND gate, the circuit is provided with the two inputs A comma B. It has one output Y, where Y should equal A dot B bar, as it gives NAND operation. So we will see how and how it gives NAND operation when we apply the various combinations of inputs. That is, these two are the input variables, and these two variables may be either both 0 or both 1, or one of uh, the input is 0, other is 1, and vice versa. So we can see that the circuit, just going through the circuit diagram, you can see that the input A is given, the A input is applied to the gate of the P MOSFET Q1 and N MOSFET Q3. Similarly, the input B is applied to the gates of P MOSFET Q2 and N MOSFET Q4. And you can see that the sources of the P MOSFET Q1 and Q2 are connected to VSS. Similarly, the drains of Q1 and Q2 are connected together, and that point is taken as output. This is also the point where we have connected the drain of Q3. And you can see that the source of Q3 is connected to the drain of Q4, and the source of Q4 is connected to ground. And this is the circuit arrangement for CMOS NAND gate with 2 inputs. And before going to see in detail the working of the CMOS NAND gate, we look at the properties of the P MOSFET and N MOSFET in general, that is when it will be on, when it is off. So a P MOSFET is on when its input is, when when the voltage at gate is 0 volt. So if you take the PMOS Q1 and this is the gate, and if at this gate we apply logic 0, it will be in on state, and then it has some resistance, so that is called as on resistance. And when the gate is applied with logic 1, when we apply logic 1 on this gate, the P MOSFET is off. The P MOSFET is off when its gate is given logic, a gate is applied logic 1, or gate is applied a high signal. So in that case the Q1 is equivalent to an infinite resistance. That means there is an open circuit between its source and drain. That means there is no connection between source and drain. So similarly, we'll look at some properties of the N MOSFET, that is when it is on and when it is off. So look at the Q4, say for example Q4 or any other general N MOSFET. So here you can see that when you apply a low signal on its gate, the N MOSFET is off. So the N MOSFET is off when a low signal is applied on its gate. Then it is equivalent to an infinite resistance, or there is a open between its drain and source. And the NMOS is in on state when a high signal is applied at its gate, and when it is on, there is a resistance called on resistance, or the gate is equivalent to an on resistance replaced between its drain and source. So these points we need to remember to understand clearly the working of CMOS NAND gate circuit. So you can see that we'll be applying the various combinations of inputs, and for each combinations we look at the working of this circuit arrangement, and we'll finally find out what is the output of this circuit for each combinations of input. For this the total working of this CMOS NAND gate is summarized into this table. So here we have shown the inputs here, and similarly the output here, and in between we have also shown the states of the on and off states of all the 4 MOSFETs. So P MOSFETs Q1 and Q2, N MOSFETs Q3 and Q4. So we'll try to apply each combinations of input, and we'll find out the output in each case by analyzing the circuit. So first we'll apply zeros for both the input, that is yellow signal for both A and B. You can see that when a low signal is applied, that is when A equal to low, that is when both the inputs are low. You can see that when both the inputs are low, you can see that this Q1 is in on state and Q2 is also on state. since they are P MOSFETs. And the N MOSFETs Q3 and Q4, so we have shown this here, the states of Q1 and Q2 we have shown here. That is, Q1 is in on state and Q2 so when both inputs are low, you can see here this P MOSFET, both P MOSFETs are on because yellow signal is applied at the gate of P MOSFET. So Q1 and Q2 are on, both P MOSFETs are. Here you see that there is a so both Q1 is on and Q2 is also on. Both Q1 and Q2 are on. Both Q1 and Q2 are on, and Q3, and when gate signal is low, when A and B are low, both N MOSFETs are off. So Q3 and Q4 are off. So in this case, the output is pulled to VSS, are pulled high by the on resistances of the PMOS Q1 and Q2. So there is an on resistance since these two are on. So there will be an on resistance for this both Q1 and Q2, and this parallel combination of on resistance will pull this output high, that is to VSS. So the output in this case is high, that is 1. Similarly, when A is low, we'll go to the second case. When A is low and B is high, so when A is low, Q1 is on and Q3 is off since it is NMOS. And when B is high, so PMOS is off since a high gate signal, and Q4 is on since a high gate signal, and this is N MOSFET. So here you can see that the output, it is connected to the drains of the P MOSFETs. So since Q1 is on, the output is pulled high again, or it is pulled to VSS through the on resistance of Q1. So in this case also, the output Y equals 1. Similarly, the third case, when A is high and B is low, so when A is high means PMOS Q1 is off and Q3 NMOS is on since A is high. And when B is B is low, so PMOS Q2 is on and NMOS Q4 is off. And here also you again see that the output, which is connected to the drain of Q1, which is on, again pulled high to VSS through the on resistance of Q1, through the on resistance of Q2. Since Q2 is on, Q1 is off, the output is pulled high to VSS through the on resistance of Q2. So in this case also the output Y equals 1. So finally we have a case where both the inputs are high. So when both the inputs are high, you can see when A is high, Q1 is off, but Q3 is on since it is NMOS, and B, when it is high, Q2 is off since it's a PMOS, and Q4 is on since it's a NMOS. And here you can see that the Y, which is connected to the drains of Q1 and Q2, you can see that both the transistors are off, PMOS transistors are off. So the Y cannot be pulled to high. So since it's a open circuit now because both are off. So since Y is also connected to the drain of Q3, and since Q3 is on and Q4 is on, the on resistances of Q3 and Q4 will pull down the output to 0. So when both A and B are high, both Q3 and Q4 are in on state, and the on resistance of these two resistors will pull the output to low. So that is why so here also this is Q1 off, and this Q2 is also off. Is off. Q3 Q4 on, and the output Y equals 0. So you can see that the output of this circuit, that is Y, equals 0 only when both the inputs are high. And you can see that this is the NAND gate operation. So I say that this circuit implements the NAND gate function. And since we are using both PMOS and NMOS FETs transistors, this circuit is called the CMOS NAND gate, complementary metal oxide semiconductor NAND gate. So this is the circuit arrangement for the CMOS NAND gate and the working of CMOS NAND gate, along with the states of various transistors for each combinations of input, and the corresponding output is shown in this table. Thank you.